We present motion scaling solutions for improved performance in high-delay surgical teleoperation. Currently, teleoperated surgical robots are used within hospitals such as the Da Vinci surgical system from Intuitive Surgical Incorporated, as shown on the right. Remote telesurgery is currently not feasible due to latency between the operator and the bedside robot. Previously developed teleoperational control under delay do not provide robust methods to counteract latency in telesurgery due to the complex tasks, unique environment, and the added importance of patient safety. Our proposed scaling solutions reduce the errors to improve patient safety, have intuitive control since the delay can change from one operation to another due to variable distances, and have simple implementation so they can be easily deployed to any teleoperated system. We conducted a user study on the Da Vinci surgical system with 17 participants to measure the proposed solution's effectiveness. Our first proposed solution is the constant scaling solution, which simply decreases the scaling factor between the master and the slave to improve accuracy at the cost of time to complete tasks. The positional scaling solution builds on the constant scaling solution and dynamically decreases the scaling as the slave approaches an obstacle. Since this requires obstacle detection, this dynamic scaling is implemented on the slave side and must be paired with 3D reconstruction techniques to calculate proximity of an obstacle. The velocity scaling solution once again builds on the constant scaling solution and dynamically increases the scaling as the operator input velocity increases. This is founded on the idea that the operator will naturally move slower when higher accuracy is required. A peg transfer task was used as sample task for the user study. The task and environment was chosen because it inherits complex motions such as handoff, regions where larger movements are safe, and yet still requires precise motions during the part of the trajectory due to the tightness of fit between the rings and the pegs. We repeat the same baseline scaling before and after the measured trials to ensure that the measurements are unaffected by the learning curve of the system and participant exhausted. Participants are only given 20 seconds to become accustomed to the new scaling solution to ensure that the best performing solutions are intuitive. Time to complete task and errors were recorded for each measured trial. A weighted error was computed for each trial by giving a weight for each type of error according to the severity. 3 example errors are shown in the videos. Our results show that 16 out of 17 participants performed best with regards to weighted error using one of our proposed solutions. Velocity scaling performed the best of the proposed solutions. Velocity scaling on average decreased weighted error by 29% at an average cost of 22% increase in time to complete task. For future work, the velocity scaling parameters will be optimized for each participant and delay to further improve teleoperated surgical tasks under delay.